Welcome to this presentation on molar mass. And molar mass is an extremely important concept really throughout the study of chemistry because it's going to allow us to move from the atomic level of looking at atoms, elements, and substances to really a more macroscopic level, dealing with grams, kilograms of reactants and products. But before we start doing some example problems with molar mass, I really want to give you just a little bit of history about how molar mass was defined, because I think it's going to be useful to our understanding. And so, back when scientists were first looking at atomic weights and masses, they defined one carbon-12 atom. Remember, this is the isotope of carbon with a total of 12 protons and neutrons in its nucleus. They defined one carbon-12 atom as weighing or having a mass of 12 atomic mass units. And that makes sense because carbon-12, a total of 12 protons and neutrons, each with a mass number of 1. Okay, that's going to equal 12 AMU. The problem with 12 AMU is, well, an AMU is extremely small. You'd never be able to count out 12 AMU, never be able to count one carbon-12 atom in the lab. What would be far more useful if we could figure out the number of carbon-12 atoms, I'm going to call that number X, carbon-12 atoms, in 12 grams. 12 grams of a sample, because then we could just weigh out 12 grams and know exactly or roughly how many atoms of carbon we have in that sample. And it turns out, using sophisticated technologies such as mass spectrometry, etc., scientists and chemists are able to figure out that this number for carbon-12 was equal to 6.022 times 10 to the 23rd. You might be saying, well, James, this is an absolutely useless number. It's gigantic. I can't really wrap my head around it. But let me show you why it can be extremely useful. Let's say we have 12 grams of carbon-12, and we know that there are this many atoms in 12 grams of carbon-12. And let's compare that to 10 grams of boron-10, the isotope of boron-10. Now, if we look at the atomic mass of carbon-12, well, we know that's just 12 AMU. And the atomic mass of boron-10 is also going to be 10 AMU. Let me put the units for you there. 12 AMU. 10 AMU. And what's interesting about this, it's really not that interesting in and of itself. It's because these two ratios are equal, right? 12 to 10, 6 to 5, however you want to say it. What this means is that if we know the number of atoms in this 12-gram sample of carbon-12, and these ratios are the same, well, we're actually going to have the same number of atoms in the boron-10 sample. Because if we multiply this number 12 by 6.022 times 10 to the 23rd to get this 12 grams like we've done here, well, because these are equal, we're going to have to do the same thing to the bottom. And so what we discover is that in 12 grams of carbon-12, there are exactly the same number of atoms in both samples. So carbon-12 and boron-10 have the same number of atoms. And because this number is so useful, we actually give it a special name. This is called Avogadro's number. And it's also equivalent to 1 mole. 1 mole of a substance. So whenever you have this many molecules or this many atoms in a substance, you've got 1 mole of that substance. And more generally, for any element or atom, 1 mole of a substance will equal in grams, so a much more usable unit, the atomic mass of that substance in AMU. So let's just look at hydrogen as another example. We know that this number here is the average atomic mass. And we know it's a little more than 1 because there are really 3 isotopes of hydrogen, but 2 primary isotopes of hydrogen. Protium with one proton, so an atomic mass of 1, deuterium with an atomic mass of 2 because of that neutron there. What this is going to mean is because hydrogen has an average atomic mass of 1.00797 AMU, that's what this is referring to here, substance in AMU, 1 mole of hydrogen is going to be equal to 1.00797 grams. And that's because when we have a bunch of these atoms, most are going to be protium, most are going to have an atomic mass of 1, some are going to have an atomic mass of 2, and so it's going to average out to this number, and this number in grams. This number in grams. And so we look at the periodic table, this number here is also not only going to be our average atomic mass, it's also going to be our molar mass, the weight or the mass of 1 mole of this atom. But we can also extend the concept of molar mass beyond the atom or element to the compound. And so let's try and find the molar mass of one mole of sodium chloride. But first we need to find the mass of 1 sodium chloride formula unit. And we know that, well, sodium has a rough atomic weight of 23 AMU, chlorine is roughly 35 AMU, and since there are 1 in each, remember this is sodium, this is chlorine, 1 sodium chloride formula unit is going to weigh roughly 58 AMU. Just add these two numbers together. What about 1 mole of sodium chloride? 1 mole of sodium chloride, we've just got 1 mole of sodium plus 1 mole of chlorine. And since we know the average atomic masses equal the molar masses of any given element, we can just add 23 grams, the molar mass, rough molar mass of sodium, plus 35 grams, the rough molar mass of chlorine, and that's going to give us 58 grams. Simple enough. But what about converting the other way? What about going from mass to moles? Well, that's just as simple. Say I have a 20-gram sample of calcium chloride, and I want to figure out the number of moles I have in my sample. Well, the first thing I'm going to want to do is I'm going to find the molar mass of calcium chloride. So the molar mass of calcium chloride is equal to the molar mass, the molar mass of calcium. So that's roughly 40.08 grams per mole, plus 2 times the molar mass of chlorine, which is 35.45, because we have 2 chlorine atoms in 1 formula unit of calcium chloride. So that's going to equal roughly, to the second decimal place, because it's taking different figures, 110.98 grams per mole. And then this is always the case. To go from mass to moles, we just divide the mass of our sample by the molar mass. So we're just going to do 20 grams divided by 110.98 grams per mole. If we look at units, the grams are going to cancel. The mole is going to come up because it's in the denominator of the denominator, which is the same thing as the numerator. And this is going to be equal to roughly 0.1802. And because of significant figures, we're going to take 2 significant figures, 0.18 moles. And there's another thing we can do with this number. We can actually go, because we know Avogadro's number, from moles to molecules. And this is another simple calculation. To find the number of molecules in a 20-gram sample of calcium chloride, all we're going to do is multiply the number of moles by Avogadro's number. 6.022 times 10 to the 23rd. You'll memorize this. Molecules, it's easy to get that confused with moles. Molecules, or we'll say formula units, maybe formula units, because it's an ionic substance, formula units per mole. And we're going to come up with 2 significant figures, 1.1 times 10 to the 23rd formula units. Cool stuff. And now to give you guys some practice with this new concept of the molar mass, you're going to get very familiar with it in the coming weeks and months. I've got 2 problems for you here. So why don't you pause this video, do the first one, and I'll see you when you get back. Alright, welcome back. Let's tackle this problem. This is probably the easier of the 2 problems. So all we need to do is find the molar mass of iron carbonate. And so first we just find the molar mass of iron on the periodic table, which is going to be, by my calculations, 58.93 grams per mole. What about carbon? Carbon is roughly 12.01 grams per mole. Oxygen is a nice flat 16.00. And then all we do is add these numbers up in the ratios in which they appear in our substance. So 58.93 plus, there's only 1 carbon atom, so plus 12.01. There are 3 oxygen atoms, so plus 3 times 16. Into the second decimal place, we're going to get 118.94 grams per mole. You'll be doing this calculation a lot in your study of chemistry. Next, something a little more complicated, how many moles of potassium oxide are there in 17.6 grams of that substance? Well, the first thing we have to do, as we just did, is find the molar mass of potassium oxide. And the molar mass of potassium oxide is just going to be equal to the molar mass of potassium, which is 39.10 grams per mole. Molar mass of oxygen, which is 16.00 grams per mole. We're going to add these in the relative ratios, so 39.10 times 2 plus 16 equals 94.20 grams per mole. And then all we're going to do is divide 17.6, which is the mass of our sample, 17.6 grams, divided by, remember you always do this, 94.20 grams per mole. So our unit is moles. Let me just punch this in on my calculator. We're going to get roughly, to 3 significant figures, 0.187 moles. Thank you very much.